Hello, good morning. So this is the Cryptography 5 session, and we have two talks in this session. The first talk is by Christian Majenz, and he will tell us about permutation superposition oracles for quantum query lower bounds.
Thank you very much. Yeah, this will be about permutation superposition oracles, and this is joint work with Giulio Malavolta and Malavolta. So I want to start out with a little bit of a motivation. So when we prove security of cryptographic algorithms, sometimes we resort to idealized models. And arguably the most important idealized model is the so-called random oracle model. So in this model, we model cryptographic hash functions as random functions that everybody has oracle access to. And if we want post-quantum security, or quantum security for that matter, we need to modify this model to the quantum accessible random oracle model, where adversaries that are quantum have quantum oracle access to the random function. So I guess the most powerful technique that has been developed so far to analyze the quantum accessible random oracle model is the so-called compressed oracle technique. So it's developed by Majenz in 2019. And from a quantum information perspective, it can be explained like this. So we view the oracle for a random function as a non-IID sequence of quantum channels, and we apply this Stein spring dilation. The good thing about this is that this oracle is very random. It's a random oracle. So the dilating register will contain lots of information about the queries that the algorithm has made. And we can then analyze that register to learn something about the algorithm and analyze its performance. Here's just a couple of things that have been done with this technique. So it was very useful for query complexity bounds and also for analyzing a whole host of cryptographic algorithms, including digital signatures, non-interactive zero knowledge, et cetera, et cetera. So here I have a small list of open problems for you in post-quantum provable post-quantum cryptography. The first three of them relate to the so-called sponge construction, which is used in SHA-3 and reflect the fact that we know almost nothing about its provable post-quantum security. And then there's a couple of other questions, especially about block cipher-related construction. These open problems, they have in common that they all are problems where algorithms have access to one or more oracles for a random permutation. So a very natural open problem is therefore to construct a compressed oracle technique for permutations. So this compressed oracle technique is super useful, so we want an analog of this for permutations. This brings me to our results. So we construct the first superposition oracle or compressed oracle for random permutations that can be used for proving bounds on the success probability of query algorithms that try to perform some search task. So here's the generic query bound theorem. So we consider an algorithm A that makes Q queries to Q quantum queries to a random permutation pi and its inverse, and outputs a value x, and the probability that that x together with its output under the permutation pi fulfill a relation R is bounded as a function of the number of queries, the sparsity of that relation, so the hardness of fulfilling it, and the domain size of the permutation. And this should really be viewed as a proof of concept result in the sense that for the first time, we are able to prove any query bound for a search task using this technique. So now, to describe how we get there, I want to first describe what makes the compressed oracle so useful for random functions. So a random function can be represented as a collection of small independent random variables, namely the different outputs of that function. And these variables fulfill that for learning one output, we only need to look at one of them, and vice versa. So this maybe seems painfully obvious, but these are the properties that enable the compressed oracle technique for query bounds. And the reason is that in this oracle simulation algorithm, there are registers dx for each input x. And to learn the output of the function under the input x, we need to look at this register dx. So in turn, we can analyze the register dx to understand whether an algorithm has information about the value h of x. So here is a picture of a query algorithm that interacts with this compressed oracle. So OF are the oracle unitaries, UI are the internal unitaries, and I want to show you how a query bound is proven with this progress measure-based technique. So we have these projectors, not P and P. P projects onto so-called database states that fulfill a certain property, and not P is the opposite. So it works like this. We remove a unitary that doesn't matter. We insert an identity here, split it into P and not P. We apply a triangle inequality. Then we exploit the submultiplicativity of the operator norm and bound some terms by 1. And voila, we have isolated the progress that the algorithm has made using its last query. And by induction, we now obtain a query bound. The reason I showed you this is because this is exactly what we would like to generalize to the random permutation setting now. So let me now describe the challenges in the random permutation setting. So naively, we would just like to repeat the success, right? So can we find a representation of a random permutation pi that is a collection of small independent random variables where learning one output requires only looking at one of them and vice versa? Well, that's obviously impossible because the outputs of a random permutation are not statistically independent. So we need to relax at least one of these two properties, independence or locality. The first and maybe most natural attempt is to give up on independence. We really like this representation of the function that as a list of outputs, so let's just try to keep that. And considering the fact that few outputs of a random permutation are approximately independent, maybe it works out. It turns out that this is difficult, so there have been attempts in this direction, including by myself and co-authors, as well as by Unruh, but somehow the devil here is in the inverse access to the permutation, because in some sense, it is fairly natural to model this random permutation by a random function, but then it's not so clear how to answer inverse queries. And of course, one can try to come up with an ad hoc method, but it turned out to be hard to prove that that works. So somehow the only path forward that's left is giving up on locality instead. So one observation is that it's easy to represent a random permutation pi as a collection of independent random variables. For example, consider any randomized algorithm that samples a random permutation. Then its random tape is just a list of random bits, so that we can use that as our collection of random variables. They are independent, but they are very useless in the sense that they have no locality whatsoever in general. So somehow a representation of pi as a collection of small independent random variables is only useful if we retain some type of locality. So learning an output only requires us to look at few of these random variables. So some partial progress in this direction has been made in the context of decision problems. So we were able to figure out a representation of a permutation as a collection of random bits plus some monolithic mess that we kind of gave up on. This collection of random bits is useful because learning one output requires looking at one particular one of them, one particular bit. And each of these bits stores information about only two outputs. So this turned out to be good enough for decision problems, but not for search. Let me now move on to describe the key ingredient that we kind of use to overcome these challenges, and that's the so-called strictly monotone decomposition. The idea of the strictly monotone decomposition is that if we have a permutation pi in Sn, then we can isolate its effect on, say, the largest value n by writing it as a product of a permutation pi prime that only permutes the values 1 up to n minus 1, and the transposition that just swaps n and pi of n. And because we just reduced the problem from a permutation in Sn to one in Sn minus 1, we can recurse and write pi as this product of transpositions that you see on the screen. And this very structured way of decomposing a permutation into transpositions turns out to have useful properties in the context of a random permutation. So the first observation is, of course, that pi of n is uniformly random, as any output of a random permutation is uniformly random. But in addition, it turns out that pi prime is independent of pi of n. You can see this by observing that pi prime is basically a permutation of the remaining domain of the permutation, and mapping that remaining domain into the remaining range that's taken care of by the transposition. So again, by this recursion, we can observe that we have now decomposed the permutation pi into independently random transpositions. This construction for a random permutation has actually a name. It's called the Fisher-Yates shuffle. And it is an algorithm to randomly permute a list of elements in an efficient way. So great, we found another representation of a random permutation as a collection of independent small random variables, but what about locality? So unfortunately, there's some bad news. It doesn't have any strong sense of locality. So to learn a value pi of x, we need to look at all values tx prime for x prime larger or equal x. However, the good news is it has some form of weak locality. So it only depends weakly on all but logarithmically many of these tx prime. And let me explain what I mean by that. So here's a picture of the strictly monotone decomposition of a permutation of 9 elements. Each of these handlebars represent a transposition. So let's compute this permutation on some input, maybe 3. So we just follow this line until it hits the blue dot. Here's another blue dot, which tells us we should swap 3 and 9, and we get the output 9. Here's another example. This turns out to be a fixed point. And for the input 1, it turns out that there's a couple of more transpositions to apply here. But in the end, we just follow each line, go through these handlebars, and we end up with the output, in this case 7. Now, let me explain what I meant by this weak dependence. So when we compute the permutation on the input 3, we observe that the first blue dot it hits is the transposition 3T3, and T3 turns out to be 3 here. But the point is, if our line crosses one of these dots, then changing T3 to any other value actually changes the output. So for example, if we change it to 2, then the output is 7. If we change it to 1, the output is 1. However, if we look at some transposition that doesn't touch our path of computation, then we can change this value to almost anything else and don't change the output. Except there's one value we can change it to, which kind of makes this transposition value relevant. This motivates the definition of active location. So we say that for a permutation pi in Sn with strictly monotone decomposition given by Tx, we say that x prime is an active location for pi on x if changing Tx prime to any other value than its current one changes the value of pi of x. And this definition makes sense because of the following lemma. For a random permutation, the expected number of active locations x prime for pi on x is upper bounded by a function that's at most logarithmic in the domain size of the permutation. Okay, so after we have seen the strictly monotone decomposition and its useful properties, at least useful for us, let me present our oracle construction. And in fact, I'm pretty sure that you have already constructed it in your head. It's basically just taking this strictly monotone decomposition of a random permutation and making it into a superposition. So here is the details. for an n-bit permutation, so a permutation of 2 to the n elements, we initialize 2 to the n registers, dx for all x, and the x of these registers has state space cx, so it has x different computational basis states. And it's initialized in the uniform superposition. And the idea is now that the content of register dx actually encode the value tx, which is the xth transposition in the strictly monotone decomposition. So how to answer queries, that's really easy. The computational basis of our register here encodes the strictly monotone decomposition of a permutation. So controlled on that strictly monotone decomposition, we can just apply the corresponding permutation. So that's fairly straightforward, but the reason why this is useful is basically the following properties that we get for this oracle. So after Q queries, there's only a number of registers that are not equal to the uniform superposition at this point that is linear in Q. And all of these properties only hold up to a negligible error. Also, after a query with an input x that's not too small, the register dx actually has flipped from being in the uniform superposition into something else. And these two properties together are actually what is useful to prove query lower bounds with this technique. So one annoying part is that there's this caveat for the second bullet that the input should not be too small, but we can fix that by applying the strictly monotone decomposition in a random order of the domain. And that because all of these oracles are completely indistinguishable from a random permutation oracle to any algorithm, and we keep the order in which we apply the strictly monotone decomposition secret, that means that any query will always be on an input that's not too small in our randomly chosen order, except with negligible probability. So now what about the progress measure-based query bound technique? So let's go back to the function case and take a closer look at what it actually does. So the key to the query bounds from compressed oracles for functions is the fact that we have a projector or a measurement that answers the question, did the algorithm ever query some x that fulfills the relation together with its output? And this measurement we can view as the logical OR of exponentially many commuting measurements where each of them for a fixed x answers the question, did the algorithm query x? And if so, is x and h of x in the relation R? So the reason why I presented the second part here is because this second measurement has an analog in our compressed permutation oracle, while the first one actually does not, because these measurements for the permutation case do not commute. So instead of trying to answer this existential question, we basically resort to a random check. So what we do is we just define a procedure of answering the question, did the algorithm query x? And if yes, is x and pi of x in the relation R for a random x? And then we give a very small bound for the probability that the answer is yes. And because that bound is very small, we can basically use the idea of the pigeonhole principle to say that for any given x, the answer will still be small. The answer will still be yes with only small probability. To give you a bit more detail, here's the query, the progress measure operator, E. It's a product of two projectors. The first projector answers the question, did the algorithm query x? And the second one answers the question, if yes, is x and pi of x in the relation R? Now, using these operators, we can prove such a progress lemma. It looks very cluttered, but let's first focus on the left-hand side. There you have the difference of the query, the progress measure operator applied to a state phi, and the progress measure operator applied to the same state, but after the application of an additional query. So that's literally the bounding the progress that's made with one query. And the right-hand side is like a sum of terms, and what's now left to observe is that each of these terms, and let's pick a simple one, is very small in expectation over x, namely n to the minus 2, order n to the minus 2. And that basically allows this pigeonhole principal argument. Now, applying this and basically finishing the analysis of all these terms, we can eventually arrive at our generic query-bound technique that I showed in the beginning. As an application, we can apply this to the sponge with the restriction of 1 round. So here's the sponge function for 1 round, and it is supposed to be pre-image resistant. That means if I give you y, you cannot find an input x that maps to y. We can basically apply our technique to this problem and get a bound as a function of the number of queries. So this technique, our generic technique, does not give us a tight bound as opposed to the concurrent work by Carolyn and Peremba that Joe talked about on Monday. But as I mentioned in the beginning, this is really supposed to be a proof of concept result that shows that permutation superposition oracles can be useful for bounding the success probability of query algorithms for search problems. With this, I want to conclude the talk. So in summary, we have now a superposition oracle for permutations that's at least fit for some query bounds. And as an application, we show that we can, for example, prove pre-resistance of 1 round sponge. Thanks for your attention.
All right, great, thanks. Thanks for the nice talk. We have time for one question.
Thanks for the very nice talk. I got one quick question about the random permutation you mentioned. So you have so in the result you say with access to a random permutation Sn to pi. I was wondering what's the cost of such oracle giving this permutation?
Sorry, I didn't catch the question.
Yeah, sorry. The question is, in the main result, we assume there's access to the random permutation oracle. And I was wondering what's the cost of this oracle? Oh, it is our assumption.
The cost?
Yeah.
I mean, the motivation is just that there are natural problems where this is kind of the most straightforward idealized model. Like, for example, the cryptographic permutation Ketchuk is often modeled as a random permutation. Mm-hmm. And this is not the plain model, but it's an idealized model like the random oracle model.
I see. Yeah, thanks.
We can have one more question.
So can you also just simulate this oracle? Like the compressed oracle technique just gives you a way to efficiently simulate this oracle.
That would be very nice. Currently, we don't know how to do that. I think that's something that's potentially possible with this construction, but I think it will require substantial like quantum algorithmic techniques to do that.
But why doesn't just like some naive solution work?
Well, actually, one thing that I can say, it's straightforward to simulate it in a space-efficient way. Because, as I said, basically only like a linear number of registers are not in the uniform superposition, so we can apply sparse encoding. So abstractly speaking, of course, there will be an isometry that approximately maps like the state after Q queries to the state after Q plus 1 queries. But to actually perform that isometry, that will require some ideas, for sure.
All right, good. And if there are further questions, then talk to Christian afterwards. Let's thank him again.